Alright, so for the second video today, this part is going to seem probably a bit easier, tree diagrams and fundamental counting principle. Once you get the gist of it, it's pretty straightforward. Okay, so here we go. Alright, tree diagrams, that's what you're going to put in the blank. Can show all possible outcomes for an event. So just like a tree, we're going to use kind of like branches and stem out, showing all of the outcomes for certain events. All right, so the first one says use a tree diagram to show all the ways Diego can order a pizza. He can choose from a thick or a thin crust pizza. All right, so that's the first thing I'm going to highlight, thick or a thin crust, because there's two types of crusts, and can also choose one topping. He can either get mushroom, pepperoni, or pineapple as a topping. Draw a tree diagram to find out how many outcomes there are. So first we start with the crusts. We say, well, he can get a thick crust, or he can get a thin crust. And from there, he can get one of the three toppings. He can get a mushroom topping, he can get a pepperoni topping, or a pineapple. And that's what he can get on the thick crust. But he can also get the same three choices on a thin crust. So he can get a mushroom, a pepperoni, or a pineapple topping on the thin crust. So then I would say, well, how many different outcomes are there of the type of pizzas he can order? He has one, so you count the farthest over to figure out how many possible outcomes. He can get 1, 2, 3, 4, 5, 6. He has a total of 6 different options of types of pizzas he can choose from. Alright, so the next one says, Cat needs to pick a snack. She can have milk, coffee, or apple juice for a drink, and apple slices, yogurt, or a cheese stick for her food. Draw a tree diagram to show all the different choices Cat has. Again, same thing. We want to think, okay, the very first information that they give us is that she can have 3 different options. She can have milk, coffee, or apple juice. Okay, so I'm going to start out with those. And sometimes you kind of have to write tiny. She can have milk, coffee, or apple juice for her drink. And I'm okay with you abbreviating. Then we would branch out, starting with milk. We're going to say, well, milk, if she chooses milk, she can have apple slices, yogurt, or a cheese stick for her food. So I'm going to write A for apple slices, C for cheese stick, or Y for yogurt for her food. Okay, well, milk gets that, but so does coffee. If she orders a coffee, she still has the choices of apple slices, cheese, or yogurt left. And same thing with if she orders apple juice, she still has all 3 of those choices. Apple slices, cheese, or yogurt. Okay, again, let's count up how many options that is. She has 1, 2, 3, 4, 5, 6, 7, 8, 9 options that she can choose from for her snack. So if she chose milk, she could choose apple slices, cheese, or yogurt. Coffee, apple slices, cheese, or yogurt. Apple juice, apple slices, cheese, or yogurt. Okay, so I want you to try number 4 on your own. Remember, you will have to write tiny and you can abbreviate if you need. Once you have the answer to number 4, raise your hand and I will come by to check it. So go ahead and pause the video. Okay, so the tree diagrams are awesome to be able to know how to do. You will have to demonstrate or draw or identify a possible tree diagram for a word problem. However, we use this thing called the Fundamental Counting Principle, or FCP, you might hear us say. Fundamental counting principle is you're doing the same thing as a tree diagram without the drawing of the tree diagram. So what you're going to do instead is you are going to end up multiplying all of the events or choices together, and that will give you that final outcome. So like on the cat problem, you would end up multiplying how many milk, coffee, juice, and then how many snacks with the amount of snacks to get you that number 9. You won't have to do all the drawings. Okay, so let's try it. It says you are looking for new sneakers. You can choose from the following 3 brands: Nike, Adidas, or Brooks, the following 2 colors, blue or yellow, and the following 2 shoestrings, white or black. Using the fundamental counting principle, how many outcomes are possible? All right, so the first thing we want to say is the brands. We have the following brands. We have Nike, Adidas, and Brooks. So how many brands is that? Oops, Brooks. That's 3 brands, okay? So that's my first part. Then I'm going to say, after I pick a brand, I also have colors. So in my colors category, I have blue or yellow, all right? So that's 2 colors, 2 options of colors. Then I have the shoestring options, and that's white or black. And that's, again, 2 options. So, using the fundamental counting principle, which says I multiply all the events or choices, I'm going to say, well, I have 3 choices here, 2 choices here, and 2 choices here. All that I'm going to do is multiply them. 3 times 2 times 2. So, 3 times 2 is 6, times another 2 is 12. My answer would be there are 12 possible outcomes for these new sneakers. Okay, the next one. When getting ice cream, you can choose from the following flavors: vanilla, chocolate, or strawberry, and the following toppings: sprinkles, cookie dough, brownie bits, or fruit. And then the following items on top: whipped cream or a cherry. How many total combinations can you decide between? So when they give you like lots of things in a list like this, and they don't specifically say use the fundamental counting principle, we know that we want to use it. So we'll start out with flavors. The flavors we have are vanilla, chocolate, and strawberry, okay? Then toppings, we have sprinkles, cookie dough, and I'm just abbreviating, brownie bits, and fruit. And then on top, so I'll write top times 2, we have whipped cream or a cherry. So look at each list. We have 1, 2, 3 flavors, 1, 2, 3, 4 toppings, and 1, 2 toppings times 2. Okay? Fundamental counting principle says you multiply all of the events or choices. So we have 3 choices of flavors, 4 choices of toppings, and 2 choices of toppings. 3 times 4 is 12, times another 2 would be what? 24. So you'd have 24 combinations of ice cream that you can choose from. All right, go ahead and try number 8 and number 9 on your own. When you are done with 8 and 9, please raise your hand and I will come around to check. So go ahead and pause the video. Okay, so the next part of this is determining outcomes. When we determine how many outcomes there are for a certain experiment or event, we're still going to use the fundamental counting principle. So we're still going to be multiplying how many outcomes to get a total number of outcomes. So the question for number 1 says you toss a coin 4 times. How many possible outcomes are there? So I like to really layer this out into how many ever coin tosses there are. So on our first coin toss, we can get a head or a tail. So on the first coin toss, how many outcomes do I have? Well, I have 2. On the second coin toss, I can get a head or a tail again. So I still have 2 outcomes on my second toss. How about on the third coin toss? How many do you think? Hopefully you thought 2. And on the fourth coin toss, how many possible outcomes are there? Again, there's a head or a tail. So each one, there's a head or a tail, a head or a tail. So we take those possible outcomes for each coin toss and multiply them together. So 2 times 2 times 2 times 2. Go ahead and multiply that out, see what you get. Okay, you should get 16 total outcomes. Okay, Number 2, Jimmy spins this spinner one time. How many outcomes are there? So all you have to do is look at the spinner to be able to see that 1 is an outcome, 2 is an outcome, 3 is an outcome, and 4 is an outcome. All an outcome means is something that will happen as a result of spinning or tossing or picking a marble out of a jar. So there's 4 outcomes for one spin. The second part of the question, though, says he spins the spinner 3 times. How many possible outcomes are there now? Okay, so here's my first spin, here's my second spin, and here's my third. On the first spin, how many outcomes does he have? Well, 4. On the second spin, how many outcomes does he have? 4. And on the third spin, how many outcomes does he have? How many different numbers could he land on? 4. Okay, fundamental counting principle says we multiply all of them. 4 times 4 times 4 is what? 4 times 4 times 4 is 64. All right, number 3, we are going to, I'm going to show you a quick video, and then you're going to answer 3 and 4.
Pick a card, any card. Actually, just pick up all of them and take a look. This standard 52 card deck has been used for centuries. Every day, thousands just like it are shuffled in casinos all over the world, the order rearranged each time. And yet, every time you pick up a well-shuffled deck like this one, you are almost certainly holding an arrangement of cards that has never before existed in all of history. How can this be? The answer lies in how many different arrangements of 52 cards, or any objects, are possible. Now, 52 may not seem like such a high number, but let's start with an even smaller one. Say we have 4 people trying to sit in 4 numbered chairs. How many ways can they be seated? To start off, any of the 4 people can sit in the first chair. Once this choice is made, only 3 people remain standing. After the second person sits down, only 2 people are left as candidates for the third chair. And after the third person is sat down, the last person standing has no choice but to sit in the fourth chair. If we manually write out all the possible arrangements, or permutations, it turns out that there are 24 ways that 4 people can be seated into 4 chairs. But when dealing with larger numbers, this can take quite a while. So let's see if there's a quicker way. Going from the beginning again, you can see that each of the 4 initial choices for the first chair leads to 3 more possible choices for the second chair, and each of those choices leads to 2 more for the third chair. So instead of counting each final scenario individually, we can multiply the number of choices for each chair, 4 times 3 times 2 times 1, to achieve the same result of 24. An interesting pattern emerges. We start with the number of objects we're arranging, 4 in this case, and multiply it by consecutively smaller integers until we reach 1. This is an exciting discovery, so exciting that mathematicians have chosen to symbolize this kind of calculation, known as a factorial, with an exclamation mark. As a general rule, the factorial of any positive integer is calculated at
The arrangements, hopefully you heard from the video, we call that factorials, and the exclamation point is the math symbol that we use for that. Really though, when you see an arrangement problem, you just want to say, okay, I know that I'm going to multiply whatever number, so 4, if it's how many different ways can you arrange 4 dogs, we're going to start out with that number they give us, of how many ways we can arrange something, and we're going to multiply in decreasing order of integers until we get to 1. So 4 times 3 times 2 times 1, just like the problem in the video. Okay, so you can do that on your calculator. Pause the video. So if you arrange those dogs, those 4 dogs, there would be a possibility of 24 ways that you can arrange them. 4 times 3 times 2 times 1, there's 24 ways. And number 4, how many different ways can you arrange these characters? Well, you have to count them up. So there's 1, 2, 3, 4, 5, 6, 7 different characters. So we're going to say 7 factorial, or what does that mean? It means 7 times, or we're going to go up or down. You're going to go down until we get to 1. Times 6, times 5, times 4, times 3, times 2, times 1. Okay, I want you to go ahead and multiply all of those out. You should get a very large number. Please pause the video. And you should have gotten 5,040. Okay? Go ahead and do the 4 you tried problems and then get them checked. Awesome work.